Hello, this is Mr. P, and today we're going to be talking about trigonometric functions. This is a subject near and dear to my heart. I do love this subject because it's used so much in upper level mathematics. I do, however, think that the way most textbooks treat this subject is they have you arbitrarily memorize the unit circle for your values of the trig functions, which memorization is good. It helps you with your speed. But I think it's also important to understand the geometric interpretations behind these concepts. So we're going to dig a little deeper into it. I know when I first encountered the subject, I had certain questions that never really got answered by the textbooks. These were questions such as, what are the origin of the trig functions? Where did these ideas come from? Why are the quadrants numbered the way they are? It would seem like you should number them left to right, top to bottom, just like we read, but that's not the case. Why are they called sine, cosine, tangent? What do the words actually mean? And why was secant the reciprocal of cosine? It seemed to me if tangent and cotangent were reciprocals, then why wouldn't sine and cosine be reciprocals? But we'll see the answer to all these questions and more. But we're going to do it by building on what we already know from geometry. So we're going to start out with an acronym that many of you are familiar with, SOHCAHTOA. And that was to remember the equations for right triangle trigonometry. This stood for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And like I said, this helped us to remember these three equations. The sine of some angle is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. And another useful thing to pull back from recent classes is the Pythagorean triples. You're actually going to see these a lot in SAT questions or ACT questions. They like to use these lengths to quickly write test questions. So it would be a good time saver to know your four most common Pythagorean triples. But most importantly, we need to know those special right triangles. Those two ones that we could tell the lengths of all the sides if we knew just one of them. So the first one of those was the 45, 45, 90, and that was if you had a right triangle with one of the acute angles being 45 degrees, then the lengths of the sides were in the ratio of 1, 1, root 2. That doesn't mean they're always those numbers, but it means they're in that relationship. So if you knew one of the legs of the right triangle, the other leg was the same measure, and the hypotenuse was whatever the length of that leg was times the square root of 2. So again, if you knew one side, then you knew all the sides. The other special right triangle was the 30, 60, 90 triangle. And those had the lengths of 1, 2, square root of 3, where 1 was the short leg. It was opposite the smallest angle. The 2 was the hypotenuse, always twice as much as the short leg. And the long leg was the square root of 3. It was whatever the short leg was times the square root of 3. So with these two special right triangles, we'll be able to draw the triangles to represent any of these trigonometric situations we're going to get into. Alright, so in addition to these, we also had certain vocabulary words or terms that we use in geometry relating lines and segments with circles. So let's look at some of those. If we take circle O, O being the center of the circle, so this is circle O. If we take any 2 points on the circle and we make a segment between those 2 points, that segment would be called a chord. Now, if that chord also passes through the center of the circle, then it is a special type of chord called a diameter. But remember that a diameter is a chord. Now, if you have a segment that goes from the center of the circle to any point on the circle, then we would call that a radius. And then for the lines, the way they interact with the circle, if you have a line such as L1 that intersects the circle in 2 points, in other words, it has to go into the interior of the circle to do that, that line was called a secant line. And then if you have a line that touches the circle in just 1 point, called the point of tangency, because that is called a tangent line. So it's important to remember these words. We will be getting into how we use them a little later. Now, for our purposes, we're going to use a unit circle. And a unit circle is simply a circle with a radius of 1. And then for our angle, we're going to use the Greek letter theta, which will be our choice for a variable to represent our angle. Alright, so now we can begin with some of our definitions. We're going to start out with, from geometry, you should remember that you can translate or rotate any angle and it's still the same angle. You can move it around anywhere you want, it's still the same angle. So we want to exploit that fact and put it in a very special location. We want to move it so that the vertex of the angle is at the origin on a standard coordinate plane. And then we're going to have one of the sides, which we call the initial side, go along the positive x-axis. And then when we think about it this way, we have the initial side starts at the positive x-axis, and then our angle opens up to the terminal side, creating our angle. And this is called standard position. Now, if the angle opens up in a counterclockwise motion, then that would be a positive angle. If it opens up in a clockwise motion, that would be a negative angle. So we're now being able to use a directional component with our angles as well. Now, you might be used to thinking about angles in terms of degrees, but in mathematics, there is a method of measuring it that is much better, and that would be radian measure. So I'm going to give you this is the dry definition of radians, but a better way to understand it is its geometric definition. Because algebraically, the radian is the arc that it intercepts when it's equal to the radius. So in other words, if we look at it geometrically, if you have your angle in standard position and you have a unit circle centered at the origin, then the arc that angle cuts off on the unit circle, the length of that arc is our theta when you have a unit circle. So if the length of that arc is equal to the radius, then that would be known as 1 radian. Radian is actually short for radial angle because it is defined by the radius. So algebraically, we can see that S, which is this arc length, is r times theta. But if r is 1, which makes it a unit circle, then we have S would be equal to theta. So that's the important thing to understand, is theta, its geometric definition, is it is the length of the arc that your angle cuts off on the unit circle. So the question is, if we know a circle is 360 degrees, which is very arbitrary, by the way, that goes back to ancient Sumerians who used a base 60 numbering system, and they thought of the year as approximately 360 days, so that's why they broke the circle up into 360 degrees. There's nothing special about that number as far as the mathematics of a circle, so there's a lot of adjustments that need to be made when you work in degrees. But radian is a much more natural way to work with angles. It has a geometric definition that doesn't require adjustments when we use it in formulas. Matter of fact, that base 60 numbering system that the Sumerians used is still seen today with 60 seconds in a minute and 60 minutes in an hour. That influence is still seen to today. So the question is, how many radians is one full circle? Well, if we know that the radian measure is the length of the arc, then it would be the length of the arc all the way around the circle, or in other words, the circumference. So if we look at it, we'd have 1 radians, 2 radians, 3 radians, 4 radians, 5 radians, and then 6 radians, and plus a little bit more. It would be approximately 6.28 radians. And hopefully by now you figured out that because circumference is 2 pi r, and if our radius is 1 in a unit circle, then the circumference is exactly 2 pi. And that is why we use pi we talk about radians in terms of pi. Although tau would be a better unit of measurement, but that is a conversation for another day. Let's just stick with the pi for now. Alright, so these are the most important ones that you're going to work with. These are the angle measures you're going to work with most often, so these ones you should know. Since pi the entire circle is 2 pi, so half the circle would be pi. So pi is equal to 180 degrees. In other words, pi radians is 180 degrees. Now notice with the radian measure, there's no unit written after that. That's because in mathematics, radian measure is the default measure for angles. If you're in degrees, then you have to put the degree symbol. Otherwise, by default, it does mean radians. So notice how pi is 180 degrees, so half of pi, which would be 90 degrees, is pi over 2. Pi over 3 would be 60 degrees, pi over 4 is 45 degrees, pi over 6 is 30 degrees, and it's just important to know those increments because you're going to be using them a lot. And as far as the quadrants are concerned, if we have angles that are between 0 and pi over 2, then they would be in the first quadrant. If we have angles between pi over 2 and pi, they would be in the second quadrant. If they have angles between pi and 3 pi over 2, the third quadrant, and between 3 pi over 2 and 2 pi would be the fourth quadrant. And that is actually why we name the quadrants the way we do. If we think of an initial side here, and then as we open up our angle, we go through quadrant 1, then quadrant 2, then quadrant 3, then quadrant 4. If you have an angle that is on the axis, then it's actually in neither of the quadrants. Notice how none of these intervals, these inequalities, none of them have the or equal to. They don't have the line underneath the inequality symbol. That's because it'll be in neither quadrant. It's what's known as a quadrantal angle if it ends up on an axis. Alright, so converting from degrees to radians and radians to degrees, we can do pretty algebraically because the conversion rate is the fact that pi is equal to 180 degrees. So just like doing conversion rates in science, we want to eliminate one of the units in favor of the other unit. So you either multiply by pi over 180 or 180 over pi, depending on which unit you want to get rid of. Now the RAD is written here for clarity to show the canceling out of the units, but normally you do not need to write the RAD to denote radians, because that is the default measure, as I mentioned. So keeping in mind our most common angles that we need to know, let's look at some of our conversions here. So if we have 135 degrees and we want to go from degrees to radians, then degree is what I want to get rid of, so that would be the one in the denominator. So I multiply that by pi over 180, the degrees cancel out, which leaves everything in terms of radians. The rest of the examples are the same way. With 540, it still works even if your angle is greater than 360. So here our degrees cancel out, and then that can be reduced down to 3 pi radians. And even with a negative sign, the algebra still works the same. Negative sign just comes along for the ride. We want to get rid of the degrees, so the degrees cancel out, and that keeps us, when we simplify, with negative 3 pi over 2 radians. Converting from radians to degrees, exact same idea, but this time we want the radian in the denominator. So negative pi over 2, we want to multiply by 180 over pi. Notice how the radians cancel out, but also in this one, the pi's are going to cancel out as well. And we're going to end up with a negative 90 degrees. Sometimes radians are expressed without pi. And if that's the case, when you do the conversion, you're going to have the radians are going to cancel, but notice how the pi doesn't cancel because it wasn't there to begin with. So you have 360 over pi is the exact value of the angle in degrees. However, that is approximately 114.59 degrees. And one more quick example. Notice our radians cancel out and the pi's cancel out, which will most often happen. And we end up with 810 degrees in this example. Now sometimes you're going to see notation that looks like this. You'll have 36 degrees. This is read as 36 degrees, 15 minutes, and 45 seconds. And it really works the same way that hours, minutes, and seconds works. A minute, in this context, a minute is 1/60th of a degree, and a second is 1/60th of a minute. You see this format in navigation a lot, latitude and longitude as well. And the conversion is pretty simple algebraically. we want to change it all to a decimal form. So the idea is 36 is our degrees. The 15 is how many 60ths of a degree I have. And the 45 would be a 60th of a 60th. So algebraically, that would look like this: 15 over 60 and 45 over 3,600. Because this is 60 to the first power, this is 60 to the second power. And when you do the arithmetic, you're going to end up with 36.2625 degrees. Alright, so it's important to understand the difference between radians and degrees. We're going to be working mostly in radians. But now we can actually get into the trig functions and what they actually mean. So I want to introduce this diagram. This is a unit circle. We're going to start out with the idea of being a unit circle. So circle O is a unit circle. That means its radius, so OT would be 1, OP would be 1, or OC would be 1. Any radius would be 1 in the unit circle. And here we have OT is going to be our initial side. And then our angle is going to open up, our angle theta is going to open up to our terminal side, represented by this line, or this segment. And then from the terminal point, I'm going to drop a perpendicular to the x-axis. This is on the coordinate plane. So P, which is our terminal point, if I drop that perpendicular, then I'm going to label this segment x and this segment y. Therefore, the coordinates of P would be x comma y, just like we do on the coordinate plane. Point T is the point of tangency, so this vertical line, line AT, is the tangent line to this circle. Likewise, line CB is the tangent line to the circle, with C as the point of tangency. Alright, so starting with theta, we want to look at this arc PT. Hopefully you remember from our definition of theta, since this is a unit circle, our theta, when measured in radians, is by definition equivalent to the length of the arc that it cuts off. So arc PT is theta when measured in radians, because we're going to be doing everything in radians. From that, we can build all of these trig functions. Notice how the angle is measured in theta, is the length of the arc is our theta, but in ancient Greece, the length of an arc was tough to measure. Curved surfaces or curved lines were tough to measure. Straight lines are a lot easier to measure. So hopefully you should remember from geometry that if you're talking about point P being the terminal point, its distance from the initial side, the distance from a point to a line, is always measured with the perpendicular distance. That's why we drop this perpendicular. So if I wanted to measure the opening of this angle, I could measure the distance from the terminal point to the initial side. So in Latin, the word sinus means opening or hollow or bosom. And sinus is what they use to talk about the opening of this angle. So this length, which is y, is the length of the opening of this angle. So therefore, it was the sinus of the angle, or in other words, the sine of the angle. Sine just comes from the Latin word sinus, which means opening or hollow. From that, everything else can be built. Because if we consider this angle here, which would be angle COP, this angle here, its relationship to theta is that it would be complementary. These two angles would add up to this 90-degree angle. So if we think of this being the initial side for this angle, so this is our initial side and we sweep over to the same terminal side, then we can think of this length, if we drop a perpendicular to the y-axis, we can think of this length as the opening of this angle. Well, this angle is the complementary angle of theta, so this sinus, or this sine, would be the sine of the complementary angle, which is also known as cosine. Cosine literally means the complementary sine. Well, notice how this segment, since we made a a nice little rectangle there, is the same as this segment. So the adjacent side, which is x, with respect to our theta, the adjacent side is literally the complementary sine. So the sine is the opening, and the cosine is the opening of the angle's complement. So again, cosine literally means complementary sine. Now we talked about PT being the length of the arc cut off by the angle, which is theta. And if we talk about the tangent line, if we look at where the tangent line is here, then our angle here cuts off segment AT on the tangent line, or segment TA on the tangent line. So the length of the tangent line that is cut off by the angle is exactly what you would expect it to be. It is the tangent of theta. Likewise, for the same reason, when we talk about the complement of theta, that would be looking at the other tangent line with respect to this angle, and that would cut off length CB, which makes CB the complementary tangent, or cotangent. And then also we talked about a line that goes into the interior of a circle is a secant line. So we can think of this line here, line OB, as the secant line. And if we look at the interval of the radius of this circle, we think of our x interval from O to T, and think of two vertical lines from O and T, then we can see the interval of this circle's radius cuts off segment OA on the secant line. So the OA part of the secant line is literally the secant of theta. The length of that segment, is the secant of theta. And if you think about this radius and working with this interval, so we have these two lines cut off this segment OB, and that ends up being the cosecant, or the secant of the complementary angle. So we can see, and an important understanding here is that the geometric meaning of these is that your angle, when in radians, is physically the length of the arc that is cut off on a unit circle. So the angles are lengths of arcs, and the trig functions themselves, all 6 of them, are lengths of segments. So if you understand their geometric meaning, then you can write equations for word problems or all kinds of problems in a much better fashion. Now this is just the unit circle. What if we have some other circle? Well, if you have any other circle, then you're going to have a different radius other than 1. But the idea here is that if we change the radius, everything else changes in proportion. So if we have half the radius, you're going to have everything else is going to be half as much, or half as long. If you have double the radius, it would be twice as much, all of the different lengths. So the idea there is that the radius of the circle is the scaling factor. So in a unit circle, x and y is literally cosine and sine, but in any circle, it's simply going to be r times that value. So if r is 1, these are our values. If r is 2, it's twice these values. If r is 3, it's 3 times these values. So in general, we can just say it's r times whatever these were. And this should make sense because this was our original equation we saw in the definition of theta, where s equals r theta. So the arc length of any circle is simply going to be r times theta in radians. And these two, first of all, you're going to see them a lot in polar equations, r sine theta, r cosine theta. You're going to use a lot in polar equations. But it's also a better way to think of the lengths of sides of triangles. So if you have any triangle with a hypotenuse r, then if you know the hypotenuse and you know the angle, one of the acute angles of that right triangle, I'm talking about if you have any right triangle, then the opposite side, which is y, is simply going to be the hypotenuse times the sine of the angle, and the adjacent side is simply going to be the hypotenuse times the cosine of the angle. So once again, you can write expressions a lot easier from your diagrams. And also for any circle, we can take these and write everything in terms of x's, y's, and r's, because we can look at this reference triangle. So for any circle, these would be our formulas for any circle. The sine of theta, if we know the terminal point, which is the x and the y, then the sine of that theta is going to be y over r, cosine is x over r, etc. for all of these. But again, these just fall right in line with what we've been doing, because notice here, if I multiply both sides of this equation by r, you're going to have y equals r sine theta, which is exactly what we already determined. So there are many different ways to calculate the sines and the thetas. I want you to have more than one way to fit the situation that you're in. All right, now let's look at some identities. We're going to start with the reciprocal identities. And for the reciprocal identities, we're going to take the same diagram that we've been working with, and I am going to use a unit circle. We're going to assume this is a unit circle. And I want to make special note of the triangle that was inside the circle, which we call the reference triangle. And then also this triangle we can make with OAT. So our first observation is going to be that OAT is similar to triangle OPD. And that's because of angle-angle similarity. Since they are both right triangles, and they both contain theta, then they have two angles in common, so therefore two angles that are the same, therefore by angle-angle similarity they are similar triangles. Well, similar triangles, we can write the proportion of the lengths of the sides. So the proportion I wanted to write would be OA, which is the hypotenuse of the larger triangle, is to the hypotenuse of the smaller triangle, which is OP, as the longer leg of the large triangle is to the longer leg of the smaller triangle. So corresponding parts of similar triangles are in proportion, so we can write these proportions. And now we can do some substitutions using our definitions of sine, cosine, tangent, etc. And we should notice that OA, from the center to where it touches the tangent point, that was the secant of theta. Since we're talking about a unit circle, OP would be the radius, which is 1. OT would also be a radius, which is 1. And OD would be from here to here. That's our x value in the reference triangle, so that is our cosine. And it sets up this formula, which then we can simplify a little bit to say that secant of theta is 1 over cosine. Then that is our reciprocal identity for secant and cosine. I could have done this with any circle. I used a unit circle just for simplicity, because notice how OA for any circle would be r secant theta, and then the radius, OP, would be the radius, which would be r, and then the two r's would just cancel themselves out. So it still works for any circle. I just use the unit circle for simplicity. And in a similar fashion, we can prove all of our reciprocal identities, which are these three. So now we can see the proof of why secant and cosine are actually reciprocals of each other. All right, the other identities that we're going to need to know are the quotient identities. So let's take a look at those. Oh, one thing before we do that is sometimes you might have trouble remembering which ones are reciprocals with which ones. So this is something one of my students actually came up with that I like, so I incorporated. We all know the SOHCAHTOA, but what they did is they added to this to remember which ones are reciprocals. And they said, since this S was sine, you can put the letters CSC there, so that sine and cosecant are reciprocals. Likewise, secant and cosine are reciprocals, and tangent and cotangent are reciprocals. I thought that was a pretty neat way to remember that, so if you want to use that, go right ahead. Now for the quotient identities. All right, we're going to start with the same diagram, same two triangles. So we've already established that those two triangles are similar, which means I can do proportions. So the proportion I want to do this time is I'm going to say AT, which is the short leg of the large triangle, is to the long leg of the large triangle, as the short leg of the small triangle is to the long leg of the small triangle. And then some substitutions. AT we know is tangent. OT is the radius, so that's 1. PD is the y value, so that is sine. And OD is the x value, so that's cosine. So cleaning that up a little, we get that the tangent can also be written as the ratio of sine to cosine. So sine of theta divided by cosine of theta is the tangent of theta. And that also does work for cotangent as well. We could use a very similar argument to prove it for cotangent. So the reciprocal and the quotient identities are very useful. Make sure you know those. You'll be using them a lot. Now, as far as trig values, the values themselves, for the special angles that are in the special right triangles, we can determine those exactly. Now, most people memorize the unit circle, because on the unit circle, as we've established, the terminal point, the x and the y represent the sine and the cosine. So any point on the unit circle, this is our unit circle, and our special angles are 30, 45, and 60, and all multiples of those. The terminal point, in other words, the point on the unit circle, represents the x value being the cosine and the y value being the sine. And if you want to remember or memorize the unit circle, by all means do that. That'll speed things up as you work problems. And I'll even give you a little known pattern within the unit circle to help you memorize it. If we look at the y values, I'll go up with the sines and I'll go down with the cosines. If we look at the y values, as I point to a value, I'm going to say how you can actually calculate it. So we're going to start with the square root of 0 over 2. We're going to start with, then we're going to have the square root of 1 over 2. Then the square root of 2 over 2. Square root of 3 over 2. And the square root of 4 over 2. And that's our pattern. Notice that square root of 4 is 2, so 2 over 2 is 1. And then the going downwards is the same pattern for the cosines. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. And as long as you know the first quadrant, all the other quadrants are simply reflections of the first quadrant. So this point, for example, and this point have the same exact numbers, except it's a reflection across the y-axis, so they have the same y value but opposite x values. So that pattern will still hold in any quadrant. So looking at, let's go down this way, you can see square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. So you got to know the magnitudes, you can calculate that way, and the positive or negatives, you just need to be aware of what quadrant you're in. Notice how in the first quadrant, everything is positive. All 6 of your trig functions are positive in the first quadrant. In quadrant 2, sine and cosecant are positive, while everything else is negative. Quadrant 3, tangent and cotangent are positive, everything else is negative. And in quadrant 4, cosine and secant are positive, where everything else is negative. And also notice we have the corresponding 135 degrees is the same as 3 pi over 4 in radians. So that's on the unit circle as well. So if that helps you to memorize these values, that's great. I want you to be able to do things fast. But in addition to the values, I want you to be able to understand how you can always figure them out. Because for that, we're going to use reference triangles. And the logic that we're going to use for this is something that will be used later on. So it's good to be able to know how to figure these out, even if you didn't have them memorized. For reference triangles, we're going to first draw our terminal side, I'll start with the sine of pi over 3 as our first example. We're going to take our coordinate plane. We have 0 degrees or 0 radians. Then you have pi over 2, pi, 3 pi over 2, 2 pi, etc. For pi over 3, that would be 1/3 of pi, pi being a full 180-degree turn. So 1/3 of pi is less than 1/2, so it's still in the first quadrant, and it would open up to about there approximately. So this would be like 1/3, and then over here would be about 2/3, and then 3/3, which is 1 pi, 180 degrees, or the opposite direction is pi. So we start out by drawing our terminal side. And then our second step is we drop a perpendicular to the x-axis. It's always to the x-axis. A very common mistake when you're working in other quadrants is to try to, like if you have a terminal side down here, trying to draw your line to the y-axis, that would be wrong. You always drop your perpendicular to the x-axis. Next, you want to label your corresponding sides. Well, hopefully you recognize that pi over 3 is the same as 60 degrees. So this angle, this pi over 3 angle, is the same as 60 degrees, which makes this a 30, 60, 90 right triangle. Which means the sides are in the ratio of 1 to square root of 3. Now, the important thing to realize here is this is not a unit circle because our radius is 2, but that doesn't matter. In this triangle, you can use any sides as long as the ratios are in this ratio. So 1, 2, square root of 3 are just easier numbers to use than working with the fractions. Also, you need to realize that the 1 in the square root of 3, in other words, the lengths of the sides, have a directional component, because this is an x value, this is a y value of this point. Whereas this hypotenuse is simply the distance that that point is from the origin, so the measure of distance is always going to be positive. So your hypotenuse is always positive. Your x and your y might be positive or negative depending on the quadrant. But in quadrant 1, everything's positive. Now once you have the triangle drawn, then you can go right to figuring out your trig ratio, which is the sine. So we're looking at opposite over hypotenuse. And with respect to this angle, opposite square root of 3, hypotenuse is 2. So sine of pi over 3 is root 3 over 2. And we're done with that problem. Now for 5 pi over 6, for example, now we're dealing with something not in quadrant 1, and let's see how we deal with that. 5/6 of pi, since I know pi is all the way over to this side, 5/6 would be almost reaching pi. It would just be, if this is 5/6, it would be 1 more sixth until we get to pi. Well, hopefully you recognize that 1/6 of pi, or in other words, pi over 6, is 30 degrees. So when we drop our perpendicular, this is again going to be a 30, 60, 90 triangle. And although 5 pi over 6 is this angle, we can use the reference triangle and the reference angle to figure out the trig ratio. And that's what's so great about reference triangles, is we can simplify the calculations. So yes, the full angle is this one here, but we're going to use the reference triangle to come up with the values. So since this is a 30 degree, we have a 30, 60, 90. So we have our short side is 1, our hypotenuse is 2, and then our long side is going to be negative square root of 3. Because remember, if you're not in quadrant 1, and this is just something to keep in the back of your mind, if you're not in quadrant 1, something's going to be negative. And since this is x and y values, we have a negative x, a positive y, puts us into this quadrant. That's why I have a negative square root of 3. But again, once you have your values, then you can go right to your trig ratio. And the cosine is adjacent over hypotenuse. So with respect to this angle, I have adjacent over hypotenuse is negative root 3 over 2. And we're done with that one. Now, for quadrantal angles, let's say we have an angle that's not in a quadrant, but actually ends up the terminal side on one of the axes. Then you're going to have a couple of different ways you can do it. First of all, just to give you a visualization of it, let's say these were all of our reference triangles. Notice how when it gets to a quadrantal angle, the triangle sort of collapses and goes away. Here again, it collapses and goes away. And notice how we're always dropping the perpendicular to the x-axis. So I'm going to animate a little bit here. You see that it goes away when you actually hit the quadrantal angles. So for that, there really isn't a triangle when you have a quadrantal angle. So my preferred method, well, the way I like to do it, is I like to actually use the unit circle in that case, because we can simply use the coordinates of that terminal point. So if it's not in a quadrant and there isn't a reference triangle, then one way to look at it would be for tangent here, for example, where we have tangent of pi. Well, I should know that this is 0, pi over 2, pi, 3 pi over 2, etc. So my terminal point is right here. And it has the coordinates -1, 0. So that's all I need to figure out the tangent. Because for any circle, we have the tangent of pi, or the tangent is going to be y over x. So in this case, our y is 0, our x is -1, so 0 over -1 is 0. Tangent of pi is 0. Works the same for any quadrantal angle. Let's look at 3 pi over 2, which would be, again, we have 0, pi over 2, pi, 3 pi over 2. So that point would be down here, and would have the coordinates as 0, -1. And this is where you do have to be careful, though, because notice how secant, if you remember from the formulas, is r over x, and r is 1. The radius of this unit circle is 1. But x in this case is 0. So you have 1 over 0, which is undefined. So for quadrantal angles, it is possible to have something undefined. Matter of fact, the tangent would be undefined either at pi over 2 or 3 pi over 2 as well. So you want to be careful with that. You do have spots where the trig ratio can be undefined. Now, this is the method I like. It's quick and easy. I also like to use the graphs of sine and cosine, but we'll see that a little later down the road. But from here on out, I am going to give you some optional topics, some other ways to look at it. Give you an alternative way. First is the alternative method for the quadrantal angles. And remember, through the animation, we saw that this was collapsing as your terminal side approached the axis. The triangle was basically collapsing away. So if we think about that collapse, let's look at what happens to the values as they reaches that destination. Well, first of all, the hypotenuse is always 1. It's always going to remain 1. And then as this fully collapses, this side is going to collapse to a 0 length. And this side will be a length of 1, but it does have a directional component, so it'll be a -1. So therefore, we can use this sort of idea of this 0 triangle collapsing to also use the fact that tangent is opposite over adjacent, which is 0 over -1, which is also 0. So it's another way to visualize it, another way you can think of quadrantal angles. I also want to show you an alternative definition of secant. We remember from before that secant is that segment OA in this diagram. Well, we could also show that that if we were to draw a tangent line to point P, the terminal point. In other words, if we were to draw this tangent line, then the place where this tangent line intersects with the x-axis, we're going to call that point S, and the distance from O to S is also the secant of theta. And to prove that, we can quickly see that OAT is congruent to OSP because of angle side angle. And the way that works for OAT, you can think of theta, and then you have the angle theta, then you have OT is the radius of 1, and then you have a right angle. So you have theta, radius, right angle. And then for OSP, you have theta, this radius, and this right angle. So then again, by angle side angle, these two triangles are congruent. And since corresponding parts of congruent triangles are congruent, that means OA is congruent to OS. And we've already said that OA is secant, so therefore OS must also be secant. So that's an additional way to get a secant function. And the final thing I wanted to show you, again, these are optional topics, is the fact that if theta is very small, then it can be used as an approximation of sine. In other words, sine was this segment PD, and theta was this arc length. Well, if your theta is a small angle, then the angle itself can be used as a numerical approximation for the sine of that angle. And that's because as this side gets lower and lower, or gets closer and closer, let's close up this angle to where P moves to P prime, for example. So as P goes to P prime, then theta is getting smaller and smaller and smaller. And the idea here is that as theta approaches 0, point P prime is going to approach point T. So the smaller the angle, the smaller the approximation, because you can see this straight line in this curved arc. As they get smaller, these two get closer and closer to being the same length. And taken to its limit, and this is planting the seed a little bit for calculus, we would say that the limit of this, as theta approaches 0, as theta completely closes up, these two will eventually be thought of as the same length. And to introduce a little notation to you, we would say, therefore, the limit as theta approaches 0 of the sine of theta divided by theta. In other words, the sine of theta was this segment, and theta itself was this arc. We can say the ratio of those two is going to approach 1. Because as it gets smaller and smaller, these two, first of all, you see, as this goes over, they actually end up becoming one and the same. They end up approaching the same point T. So we can say, therefore, the limit as theta approaches 0 of sine theta over theta is 1. All right, so throughout this, we did find out what the origin of the trig functions were, why the quadrants were numbered the way they were, why the names sine, cosine, secant, tangent are used, and we looked at reciprocal and quotient identities. So with that, and we're done.